Perfect. So I'm Andrea Vargas. I'm part of the DevRel team at Avalanche. So my job here is trying to make developer life easier. And today we're going to talk about EVM Stateful Precompiles. In other words, is how you can make your EVM more powerful, enabling more functionality. So before we start, it's just like thinking about blockchain. I know you all are familiar with blockchain. Who consider themselves a developer here? You, okay, great, some sort of. Cool, so a blockchain, we can see them as a replicated state machine. And what this means is that you can consider a blockchain to be like on a certain state, and after processing one block or certain function, we will be transitioning into another state. So what the virtual machine is, it has or defines a full semantic on how these transitions are going to be made. So it has the full logic on how you can go from state 1 to state 2. And a subnet is the Avalanche way to have your own set of validators agreeing on your own blockchain. So the thing here is that what we will be doing right now is actually modifying the logic on how the virtual machines handles these state transitions. So a virtual machine is basically, and for those familiar to object programming or oriented programming, you can think of a virtual machine in the same way that you can think of classes and objects. So you can have a virtual machine class, and then you have different instances of the same virtual machine. So you can think of the EVM, for instance, that you have different instances of the same virtual machine. So you have Ethereum, you have Avalanche C-Chain, you can have Subnet EVM. So right now, because we are modifying the EVM, the virtual machine itself, we will need a Subnet EVM to do that. So we are using that VM to modify it. So the first thing is, when we think about like the different layers of a blockchain, we can think of Ethereum, for instance. We have the consensus layer, which is just like the protocol kind of message passing, where you need to agree on certain state on the different nodes of the blockchain. And then we can think of the execution level, where it's all the logic is going to go there. That is where the EVM goes. And after that, we have the application level or the smart contract level. So when you program something in Solidity, you are programming at the application level. If you want to modify, and what we're doing right now is we're modifying the EVM or the execution layer. So for Avalanche specifically, we have different layers. So what we can do is not just one single chain, as we just saw with Ethereum, but we actually have like a common network peer-to-peer. And on top of that, we have the consensus that is being agreed on those different states. So Avalanche is not just one single blockchain, but you can have different execution environments or different execution virtual machines, where you, on top of that, will be able to use that interface or that transition logic in different ways. So for instance, we have EVM execution layer, and on top of that, you're going to deploy in Solidity. This is the case of the C-Chain or any other Subnet EVM. But we also can have or support different virtual machines, such as WASM one, where you can program in Rust in another chain, or any other chain that you can think of. And even more powerful, if you want to customize your virtual machine or the logic on how you will be optimizing the resources of the computers that you're using, you can actually build HyperVM. This HyperVM uses HyperSDK, which allows you to have your own virtual machine built from scratch with every primitive that you would like to have. So the thing, virtual machine is being designed with performance as its core. So if you want to have like 100,000 of transactions, that's something that the HyperVM can achieve. But for now, and for this workshop, we're going to be focusing on the EVM part specifically. So this part is the thing that we will be modifying. We're not talking about the application level, where you, like usually developers code on Solidity. Has any of you developed an application, a dApp on Solidity before? Okay, great. So right now, someone has ever modified anything at the EVM level? No? Okay, great. This is going to be the first time, which is nice. So this is really powerful, and you might be wondering, why would I want to modify the EVM if I can just build anything on top, right? Because like the EVM is meant to be a blockchain that is Turing complete, which means like you can basically program everything that you could ever program, I don't know, like in Python, C++, whatever other language, but you can program that as well in Solidity. The thing is, we will see why would make, and what kind of use cases and what kind of features you can enable by modifying the virtual machine. So when we think about the EVM, we have different kind of state transition that we can that we can perform. So we can have an external own account, which means a normal wallet or a personal own wallet that modifies or interacts with another external own account. We can also have the interactions with contracts and contracts with contracts. So right now, because we will be focusing on the part of the EVM itself and the precompiles, we're going to be focusing on the contract side. And I was saying, like, why would you need to modify the EVM? Well, if you think of this EVM Turing completeness, you can practically say, like, I can program anything, right? Like anything I can imagine. But the thing is, like, yeah, you can do it. You can actually start with, like, I don't know, like real simple math, which is going to be easy. It's going to be cheap. It's going to be just fine. But when you are trying to do more complex models, you require sometimes a little bit more power. It can be like as non-performant, or it can be really expensive to actually start implementing that code on Solidity. Something like use cases that you can think of is like implementing some machine learning models or implementing some cryptography. So right now, if you want to code that in Solidity, you might not have the same libraries that you might have in other languages, such as Golang. And it's also computationally intensive, which is not suited for performing on the Solidity level. So another thing is, like, for instance, and one use case that has been implemented as a precompile in the EVM, such as in Ethereum specifically, is cryptographic functions. Why? Because first, you don't need to reinvent the wheel and you can just use libraries that are currently existing in other languages. And of course, it's dangerous for you to implement your own cryptography. So this is also some reason why you would like to start using existing tools instead of developing your own. So you can think of the EVM precompiles just kind of a wrapper, Solidity wrapper around a Go implementation, which is really nice because that way you will have a Solidity interface that will allow you to interact with your contract, with your applications, but you will be executing Golang code, which makes it super powerful. So basically, it's about like performance optimization. You will have, like, Solidity is not as performant as Go. You can also use existing libraries. This is great for security. And if you want to add some special features that you don't want to implement, or just struggle like implementing those when you can use existing ones. And also, we use that for interoperability. In fact, we're going to have another workshop today about Teleporter, which is our cross-chain communication protocol. And that uses some precompile that is implemented in our virtual machine level on the EVM. But it's also compatible with other virtual machine or execution environments. So that way, when you modify at the level of the virtual machine, you can be able to start communicating different kinds of execution environments. So you can think of a precompile, some sort of a shortcut to execute code that is implemented by the EVM itself and not by a Solidity application. So because it's in the EVM, inside the EVM, there is not any bytecode associated to it. So whenever you deploy your contract at the application level, you're going to get a bytecode. This bytecode is then interpreted by the virtual machine to execute certain actions and perform that state transition. But in this case, there is not going to be any kind of bytecode associated to it, but it's going to be built inside the virtual machine. And also, whenever a precompile is called, the EVM just checks if it is a precompile, and if it's a precompile, then executes the Golang code Otherwise, it's going to be loading the bytecode and just reading from the like that bytecode with the specific opcodes that you currently have on the EVM. So something important as well is that when you create your own precompile, you got to decide how much of the gas is this going to be costing. So this is the interface that a precompile contract implements. So it says like require gas. So you don't need to follow the prices of the gas of the current opcodes because that operates on bytecode. But right now, because you are interacting at a lower level, you can specify how much gas is this call gonna cost. And then you have the function of running the precompile, which will handle the logic of the precompile. So for instance, this is how you interact with a precompile, and it has this address associated to it. As you can see, this is a really specific address. These are addresses that are reserved for precompiles. This is not exclusive to Avalanche, but it also happens in other EVMs. So as I said, like cryptographic functions are some use case that has been implemented in this specific way as a precompile. And for instance, we have a SHA-256, and then we implement that and deploy that to a specific address. We will see how we can specify that address. And then we call that as a normal contract. We just import the interface, and in here we set the address, and we just can start calling that function that is hash with SHA-256. So how does that look in the Go part, in the Go code? Well, it's basically, we'll probably see this clearer in the code in a few. But right now you can see that you are importing this library. This library is from Go. So all the code that you are writing is Go, and here you implement, or here you use the SHA-256 function to start hashing the data. So why this is important? So imagine you want to start using some sort of zero knowledge proof cryptography or any kind of advanced cryptography. Then you just implement a library and just start using it as a precompile. The thing is, like, because you need, you're modifying the EVM, which is super powerful. So you need all the network to agree that you have the same execution environment. Because otherwise, if you say, like, if you perform or you call this action specifically, and you need to pay some specific gas, then we all in the network need to agree on that specific version on how we're going to transition from state 1 to state B. So that way, if every time someone wants to implement a precompile, they need to be a network upgrade. So, or you can launch, and the magic here with Subnet EVM and with the subnets is because you can launch any chain that you want, you can customize that as however you want. And then you can have your own custom precompiles in each of these chains. So, but this is just a precompile. So a stateful precompile, which this part is actually specific to Avalanche because of this feature that you can customize your own chain. This stateful precompile injects a state to the blockchain. So it has access to modify any kind of the state that we were transitioning into some other state directly. It's not like just computing some functions as we have with SHA-256 or with any other cryptographic functions, but it actually can modify the state. And this is completely powerful in the sense of what you can start doing and how you can handle these kind of state transitions. So this is how it looks like the interface of stateful precompile. So you basically have the run function, and here it's a little bit different. In the previous one, you were submitting the amount of gas that it requires. Well, here you supply some gas, and afterwards you return the remaining gas after the execution. So it's a little bit different, but something important to notice is this precompile accessible state, which is the access to the database that we are using in our blockchain. So here we can see the type accessible state, which has this get state DB. So it will load the state DB and can actually modify that database that we are using behind that. So what kind of examples that we have for stateful precompiles could be who is allowed to transact or to deploy any contract in the blockchain. So you, instead of controlling that at an application level, which is something that usually happens, like I need to whitelist you, right? But instead, imagine you are building an open, I don't know, a gaming subnet, and you don't want anyone to come with an NFT drop of something that has nothing to do with your chain to deploy a contract there. Well, while in some other chains, such as in Ethereum, let's say, or the C chain, you cannot restrict who's deploying a contract, but you can deploy who access to your contract. In here, you can control the whole infrastructure, which is really nice for applications such as institutional adoption that require any client that is coming or interacting with your blockchain to, I don't know, like pass some KYC process before start interacting with it. Some other thing is as well, like the native minter, it's an address that can mint native tokens, and that tokens can follow some specific logic around how this is going to work. Another thing is like the fee config. Anytime you want to modify how the gas is being configured in your network, you usually require a network upgrade, but in this case, you can set that a contract handles that kind of thing. So where do you put this information on how you create a new chain? And we're going to go through it in a bit. Well, this goes in the Genesis block. So when you are configuring a Genesis, like a new chain, you need to specify what the configuration of the whole Genesis or the whole blockchain is going to be. So the Genesis block usually contains all this information. It will have the gas configuration, the allocation of the funds at the very beginning of the where the subnet or the chain has been launched, and you can have there as well the precompiles. If you want to modify a precompile afterwards, then you need an upgrade signal, so you can know every validator is going to activate in this specific time this specific precompile. We're going to see that in a minute. So we're going to go for the demo. Any question so far? Okay.
Yeah. So when you said it compiles to WebAssembly, is it specifically something like WASI-32?
So in this case, I guess you refer to this one, right? The WASM. So this is a specific virtual machine that is being built. But yeah, so the idea of Avalanche is that it can handle any environment. So if you want to do some specific implementation or execution environment for WASM, you can do it.
Yeah, the reason I was asking about that is because I see you're implementing this in Go.
Mm-hmm.
I'm wondering if this could actually be implemented in any language that can compile down to WebAssembly.
Yeah, absolutely. Yeah, you can do it. So it depends actually on what you want to build, but yeah, the idea is that you can customize every level of it. We actually have this HyperVM. Like you can modify all the levels or all the layers where you want to do, even like how you, I don't know, like process blocks. You don't even need to have blocks. That's how flexible the SDK is, so yeah.
So on HyperVM, what is the VM actually executing in terms of like steps?
So the HyperVM functions with some sort of actions, and it has a database, right? So this database is just key value pairs, and then you have the actions that have some effect into the database. So it depends on actually what you want to build. The WASM one is actually being built as well in HyperSDK. So you can have like any engine there. But yeah, it's kind of an opinionated framework that you can start using. Yeah.
So the HyperVM is basically acting as it's a key value store for, and when you say actions, is that something that like is interfaced with through more of a SQL-ish interface, or when you're saying actions, is that more of like doing actual code execution on the data?
No, it's actually doing code execution, yeah. You define how this is going, like, so for instance, we have a virtual machine that only does like sending tokens from one to another. So the action is just transfer, you know?
And then for interfacing with that, is the SDK language dependent, or is there a language independent
So right now, HyperSDK uses Golang. So if you want to implement in Go, it's yeah. So you actually need to clone the repo because it has like a lot of of section, but yeah, you have a Go package for that, and you can start modifying the different actions. What I recommend you to do to start like playing around is just go to the repo. I can send you that later, and just first start testing that. You will have, because this is not an EVM, you will need to have your own CLI to start interacting with it. You can build that inside with the different actions that are going to be called, and just start playing around a bit. But yeah, so the actions actually have this kind of modified state access of the database like that. But yeah, there are some plans of like different teams building around HyperSDK, different kind of architecture, different kind of structure, virtual machines. So it's not a product that is actually ready for production yet, but you can start testing that. Give us any feedback that you have. It's going to be interesting for you if you want to try that. Cool. Any other question? Cool. We're going to see how we can do this EVM thing. But before that, if you want to keep learning more about these, how you can build in the different stacks of the layers that I show you, we have, first of all, we have the Academy, where you can learn about Avalanche fundamentals, like what a subnet is. Like this is not getting too much into the code, but it gives you a lot of sense of blockchain fundamentals and Avalanche-specific topics. You can also have the subnet architecture, which is going to learn, where you're going to learn how you can start building your own subnets, and the customizing EVM, which is one exercise that we're seeing today. And we have many. So if you want to scan this QR code, you will be able to get into the different platforms that we are, and you will be able to find there the Academy. Every time you finish a course, you will be able to get your own certificate that you complete the course, and we will be looking for feedback as well for that. If you have any, please let us know so we can start improving these for every student that comes to the Academy. So let's do this thing, because we wanted to make it easier for the Academy students to start. We have a repo which is precompile EVM, so we're not working directly with the subnet EVM, but we're working with precompile VM, which is basically just a way to abstract all the complexity of the subnet EVM and start working just in the precompiles. So we have this repo, and if we go to the branch of the Academy, we're going to start working from there, because as is a code that is being modified all the time, this gives you like just a version to start with to be compatible with the Academy. One thing that we have done for you is to have code spaces, which are just some sort of environment that has everything installed on it, so you don't need to actually install anything to start. You just start a new code space, just like a kind of container kind of thing. I already created one. It's going to take some time to launch, but once you have it, we can join here, and you will be able to send these, instead of being in the browser, you will be able to send that to your VS Code in here, open in VS Code, and you will be able to just start with it. I already have that open, so I'm just going to close this one, and here we go. So I have right here, I have the steps on how you can start actually doing this. So you start the code space, which is what I already did. And what you need to do is create the Solidity interface. So to create a Solidity interface, it's just like a regular interface on Solidity. Let's see, contracts, interfaces. Here we'll find different interfaces. So for instance, the SHA-256 interface just look like this. You provide a value, which is a string, and it will return a hash, which is bytes 32. If you want to implement different kind of functions, you can just, for instance, IMD5, the interface for MD5, returns a byte 16. So it's really just the interface that you need to code. And after you code that, and I'm actually running this command for compiling the interface, so we can actually see the changes. So right now, when I clone this, it actually has the implementation already there. So I want to show you what are the changes that you need to make for your SHA-256 to work. So you first need to compile the interface. SHA-256. As I said, because this is just a container, it has everything inside that you will need. Oh, hold on. So I need to cd into contracts. And now we compile this. OK, now it's compiled. The second step is generate the precompiled boilerplate contracts. So this will give us just basically everything we need for the precompile. So we put here where we want our output. My precompile is going to be type SHA-256. And my interface is going to be SHA-256.avi. And I think that's it, right? Precompiles. Yes. Oh, OK, I need to cd back to the start, and then scripts. OK, so this is compiling. It's using some specific subnet EVM version. From here, we will get all the files generated. So it will generate this directory for you, containing all these different files. We'll go through them in a minute. But yeah, as you can see, because this already has the answers on it, we will be able to see the changes of the contract that are being modified in this step. Once it finishes loading, it will give us everything we want to know. So, but right now, I can start showing you what are the things and where the logic of the specific precompile and where the libraries actually implemented. So in contract.go, we can see that we have the everything basically just there. This is something that is just the output of the generic precompile. And it's going to give us the different way where we can pack and unpack the different bytes where we are using. So the virtual machine uses bytes to communicate with the interface. So you need some sort of way to start interfacing between those two. So we have this pack and unpack. That's what this part does. And here with the function hash with SHA-256 is where we will be able to start doing these kind of outputs. So basically, this is the only line that will allow us to implement this function of the crypto SHA-256 that we have right here. So up here, we have the library implemented. This is in Go. This is just a function that comes from the Go packages. Right now, it is OK, right here. We can see the changes, right? Like, let's go to contracts, which was the one that I was showing. And this will allow you to see the different changes that we made. So we did the import here of the library. And then we just need to actually say what the output is going to be of our contract. And with just that simple line of code, you will be able to start using SHA-256 from a precompile. And now I'm going to show you where you need to actually put which address is going to be associated to this precompile. So if you go to module.go, you will have the contract where you define this specific address. Contract.go. So you just need to make sure whenever you start putting these addresses that you are not repeating the same address to different precompiles, because that way it's gonna you cannot have two precompiles associated to the same one. The other one, the other important thing that you need to do in module.go is to specify which keyword you are gonna be using, which is this config key. This config key is the one that you will be using in your Genesis block to actually enable this precompile at some specific time. So you need to modify, and if we go back to our instructions on how we need to do this, we already have the boilerplate contract. We need the contract completed with the function that we already did. We did the module.go, and we need also to include the precompile in our list of precompiles that are going to be included in our virtual machine binary. So we will find that in our plugin folder, and it's going to contain some main Go file. This is where you add the different precompiles. Okay. So whenever you have these precompiles activated, you will be able to, added, you will be able to build your virtual machine. You're going to do that. I'm going to just revert all changes so we can have all the changes just like with the different answers that we already had. And we will just build the VM terminal. The script build sh. This is building the binary of our virtual machine. And once that we have that, we need also to specify the Genesis block, which just looks like a JSON file. This is how a Genesis block looks like. It has the chain ID. It has the different information of forks that you can implement or changes that you can implement. It has all the config of the fees. And it also has, this is where our precompile gets activated. It has the block timestamp at 0 because this is going to be activated at the very beginning when we launch our subnet. And we have the different kind of information of allocation and information about on the different side of the different information of the Genesis block. So with this information, our binary of the virtual machine and with the Genesis block, we will be able to start a new network and deploy our chain. So to start our chain, we will be using Avalanche Network Runner. This will run 5 nodes in our chain. So the first thing is to start the server. This server is just to listen any instructions or any deployment that we will be doing. And once we have the server, we need to specify what we want to do with that server. In this case, we'll be running Avalanche Network Runner. We're using some specific endpoint. We're launching 5 nodes with a blockchain specification of the Genesis block that we want to use for this specific instance of the virtual machine that we just created. Any question here? So good? Okay, great. So this is going to take a while. It's building the chain, and it's communicating to our server just to start those 5 nodes, agreeing on this different state. We're having our nodes up, and something that I'll be preparing while this gets set up is our wallet, so we will be interacting with our precompile. So to set that up, we will be using Remix just to interact with the precompile because, as I said, this is the Go implementation wrapped around some Solidity interface. So what we need to do is this interface that we created before, which is contracts, interfaces, SHA-256. We're going to copy these. We're just going to put it in our Remix. SHA-256.sol. We paste that in here. We compile. And now that this is becoming healthy, we now have 5 nodes. So we have 5 RPC endpoints that we can connect to our network. So we will set our wallet to work with this chain. We are using core. So you'll need to go here in custom, add network. We add this RPC. We need to make sure our RPC ends up in /RPC. And then we can just put the name of the network, test hack house. Chain ID. The chain ID is some information that you get from the Genesis block, which is the one that we put in our, when we were running that, and it's at the very beginning. So our SHA-256 is going to be 99999. So we put that in our wallet, and we can go test, save. So right now we are with our wallet, and the address that has allocated every single penny here is this address. This address, I have it loaded here. So I can see I have these tests that I can start playing around. And something important is to interact with our precompile, we just need to load that interface at the specific address that we mentioned. So the address is, as we can remember, in the module.go. We see the address here. We just copy it. And we need to make sure we are connected to our specific chain with the injected provider in MetaMask. And we can load the interface that we just pasted in here, just at this address. And we will be able just to start using the hash and getting the hash of this specific text that we sent. So as you see, this is easy in the sense that you can, if you know how to code in Go, you can start doing this implementation, have access to different or even more complex libraries, or you can have like different functionality that is going to be more performant than if you implement this in Solidity. And yeah, that's it. It's actually pretty easy to launch your own chain with this. I suggest you to play with this around. As I remember, this is the QR code where you can get to the Academy. And yeah, any question regarding all this? It's all good? Is there a link to the repo in there? Sorry? Is it? Yeah, in here you can find the docs as well and the GitHub repo. In here you will find all the Avalanche repos, and you will just need to find the precompile VM one, so you can start just forking that. And yeah, it's basically just these steps that you need to follow in order to actually have that. Yeah, it's pretty easy. But anyway, you can get as complex as you want, depending on the implementation that you want to build. But yeah, it's there. I hope you liked it, and thank you so much.